Hello everyone, this is Divya, working as assistant professor in Triple Department at St. Peter's Engineering College. So in the last classes, we discussed about the different topologies in the production of solar thermal power generation. In this class, we will discuss the basic operation of those topologies. So coming to the first one, the parabolic power plants are the only type of solar thermal power plant technology with the commercial existing operating systems until the year 2008. So, in capacity terms, 355 megawatts of energy, that is electrical power, are installed in the California, and plenty of new plants are currently in the planning process in other locations also. So the parabolic through collector consists of large curved mirrors, which are shown in this diagram like this. These are the large curved mirrors, and consisting of concentrate the sunlight by a factor of 80 or more to a focal line, that is the middle line. So parallel collectors build up a 300 to 600 meter long collector row in a single row, that is the length of 300 to 600 meter. Those are built up, and a multitude of parallel rows form the solar collector field. When we are placing the number of solar collectors in the parallel, they will form a solar collector field. The one axis tracked collectors follow the sun. The collector field can also be formed from a very long rows of parallel personal collectors. So in the focal line of these, it is a metal absorber tube, which is usually embedded in an evacuated glass tube that reduces heat losses. A special high temperature resistive selective coating additionally reduces the radiation and the heat losses. So the thermo oil flows through the absorber tube. This tube heats up the oil to nearly 400 degrees centigrade. The heat exchanger transfers the heat of the thermal oil to a water steam cycle, which is also called as Rankine cycle. A feed water pump then puts the water under pressure. So finally, an economizer, vaporizer, and a superheater together produces superheated steam. So this steam expands in a two-stage turbine. Between the high pressure and low pressure parts of the turbine is a reheater, which heats the steam again. So the turbine itself drives an electrical generator that converts the mechanical energy into electrical energy. The condenser behind the turbine condenses the steam back to water, which closes the cycle at the feed water pump. So it is also possible to produce superheated steam directly using solar collectors. So this makes the thermo oil unnecessary and also reduces cost because the relatively expensive thermo oil and the heat exchangers are no longer needed. And however, direct solar steam generation is still in the prototype stage only. So coming to the true power plant efficiencies. So this is the total operating diagram of the true power plant, parabolic true power plant, and this is a hot tank and this is a cold tank, and this is the heat exchanger. This is the turbine. This turbine operates the generator, and this is a cooling tower. This is a condenser tank. So the efficiency of a solar thermal power plant is the product of collector efficiency, field efficiency, and its steam cycle efficiency. The collector efficiency depends on the angle of incidence of the sunlight and the temperature in the absorber tube, and can reach the values up to 75%. So field losses are usually below 10% only. Altogether, solar thermal through power plants can reach annual efficiency of about 15%. So the steam cycle efficiency of about 35% has the most significant influence. The central receiver systems such as solar thermal power plants can reach higher temperatures and therefore achieve higher efficiencies. So the next one is parabolic through system. So parabolic through system image is the this one. This is the operating image. This is the operating image. This is the actual image which is located at a particular location. So this is the parabolic through system. The number of mirrors are located where this axis represents the total sunlight concentrating on a midpoint. So this is the parabolic through system. And coming to the next one, that is solar power tower system. So here this diagram shows the solar thermal tower power plants. Here at the middle a tower is placed and around that like a concentric circles the PV cells were placed, the PV plates were placed. So the reflection can be incidented on the tower like that these PV plates are placed. So in solar thermal power plants, hundreds or around thousands of large three-axis track mirrors are installed around a tower. These are slightly curved mirrors are also called as kilostats. A computer calculates the ideal position for each of these, and a motor drive moves them into the sun. That means which can be moved based on the sun rays to collect the sun rays. So the system must be very precise in order to ensure that the sunlight is really focused on the top of the tower. So it is here that the observer is located and this is heated up to the temperatures of thousands degrees centigrade or even more. So the hot air or molten salt then transports the heat from the observer to a steam generator and which is superheated water steam is produced there, which drives a turbine and electrical generator. So, in the same way as the parabolic two power plants. So, only two types of solar tower concepts will be described. Those are open volumetric air receiver and pressurized air receiver. So, coming to description about the solar thermal tower systems. So once again, I'm repeating the solar power tower system's description. So a power towers, which are also known as central tower power plants or heliostat power plants. These can be designed to capture and focus the sun's thermal energy with thousands of tracking mirrors, which are also called as heliostats, is roughly a 2 square mile field. So a tower resides in the center of the heliostat field. The heliostats focus concentrated sunlight on a receiver which sits on top of the tower. So within the receiver, the concentrated sunlight heats molten salt to over 1000 degree Fahrenheit or 538 degrees centigrade. The heated molten salt then flows into a thermal storage tank where it is stored, maintaining 98% thermal efficiency and eventually pumped to a steam generator. So the steam drives a standard turbine to generate electricity. So finally, we can use two types of solar power tower systems, that is open volumetric receiver with steam turbine cycle and a pressurized receiver with combined gas and steam turbine cycle. Here we can see the diagram of a operation of the steam turbine cycle. So here in this direction, the heated salt, the heat will be produced here and like this. So here, these are the which is received by the power tower. And next we will go with the solar dish or engine systems. So coming to the solar dish or engine systems, we can say that the systems consist of standalone parabolic reflector that concentrates light onto a receiver position at the reflector focal point like this. So this can reflect the reflector focal point and coming to it can be also called as Disk Stirling systems, which can be used to generate electricity in kilowatts range. A parabolic concave mirror, that is, the dish concentrates sunlight. The two-axis tracked mirror must follow the sun with a high degree of accuracy in order to achieve the high efficiencies. In the focus is a receiver which is heated up to 650 degrees centigrade. The absorber heat drives a Stirling motor, so which converts the heat into motive energy and drives a generator to produce the electricity. If sufficient sunlight is not available, conventional heat from either fossil fuels or biofuels can also drive the Stirling engine and generate electricity. The system efficiency of dish Stirling systems can reach 20% or more. Some dish Stirling systems prototypes have been successfully tested in a number of countries. So, however, the electricity generation costs of these systems are much higher than those for crew or tower power plants. And only series production can achieve further significant cost reduction for dish scheduling systems. So, this is the pedestal and face support structure of the dish, and this is the mirror faces and power conversion unit. Here we can place the power conversion unit. This is the supported home, and this is the drives. This is the actual location of solar dish or engine systems or dish scheduling systems in a particular place. And next, coming to the compact linear Fresnel reflector. Linear Fresnel reflectors use long, thin segments of mirrors to focus sunlight onto a fixed absorber located at a common focal point of the reflectors. So these mirrors are capable of concentrating the sun's energy to approximately 30 times its normal intensity. This concentrated energy is transferred through the absorber into some thermal fluid. The fluid then goes through a heat exchanger to power a steam generator. So the fluid can flow through this one. It can power the steam generator. So the output here is the electrical energy.